I am from Southwest Research. Robert Clark was supposed to give this talk today, but the Cygnus mission is hopefully going to launch soon. They were scrubbed again today, I understand, but everything's go for tomorrow, I think. So I'm going to present for him. I'm going to talk about telemetry storage systems, and I'm going to compare MMS and Cygnus. So MMS is a magnetospheric multiscale, and Cygnus is the Cyclone Global Navigation Satellite System. So they're both constellations of satellites. They're fairly significantly different approaches. So MMS is a currently operational mission. It consists of 4 large observatories. Each of the observatories is the same. They fly in a tetrahedron and work together to collect data on the magnetosphere. Relevant to the discussion here, we talk to one observatory at a time, so those ground contacts are managed over time across all the spacecraft. We typically have an hour contact each day, and the goal of this is to discover some detailed physics associated with the process of reconnection, and all that is going well. Mission is moving along nicely. For MMS, the organization that we have is the Central Instrument Data Processor, the CIDIP, manages a file store, a mass memory module, and connects to a number of instruments in the instrument suite. So we have the field system, FPI, HPCA, and so on. There are several different instruments that need to be talked to. We collect that data into the CIDIP and store them in the files. I'll explain a little bit more about how all that works. Our CIDIP runs on a Spark processor, and as I said, it stores the data for the science instruments. One of the observations is that the instruments can collect far more data than can be sent via the downlink, so we need to do something to manage that process. So here's kind of a picture of the orbit. So the orbit takes the set of observatories out into the magnetosphere, and so we have marked here this region of interest, and so we break the orbit into a slow survey portion when we're not expecting to see much of great interest, and the region of interest where it's possible to see reconnection. And then we identify a portion of the orbit here with these highlights for what we call burst data. And it turns out while we're in the region of interest, we do collect that burst data continuously, but we can't bring all of it down. So on the ground, scientists will select some portions of that data to bring down to the ground. And then we'll reuse those files and overwrite them. I guess we do collect relatively, moderate resolution data. We call this the fast survey data. And then over here, we collect slow survey data. All the survey data is brought down to the ground. So for MMS, we have decided to use CFDP. We've heard a little bit about that already today. I'm not sure that we've talked too much yet about the different classes, but we do have Class 1 and Class 2 for unreliable and reliable transfer for MMS. We plan to use Class 2, and we have been using it. We have Class 1 as a backup, but we really haven't used it. We do not use Class 3 and 4, which include waypoint support, but we have no need to do that, so we don't. File transfer can be initiated automatically on board or manually from the ground. So I think that's everything there. So why would we use CFDP? We use it so that we can manage the ground contacts effectively, and so that we don't lose data. So we want to recover from problems in transmissions, and CFDP lets us do that. So part of that thinking is that the CFDP will help us to automate the routine delivery process and simplify operations. And in fact, we've seen that it's worked very effectively. In addition, we were already taking advantage of the fact that CFDP is a growing process that's being used for data transfer. And so we were kind of piggybacking on work that was already done and mechanisms that were already in place. So how does this work? CCSDS, Space Packet Protocol, is the underlying protocol. We're using Class 2 with deferred NAC. We have Class 1 as the backup. We're using the NASA Goddard CFDP library, which implements the protocol through state machine process. It interfaces to the user applications, the virtual file store, and the communication system, as we can see over here. So this is the piece that we get from Goddard, and then these are the external entities that need to be communicated to. So we consider the SIDIP mass memory as a virtual file store. We do not have a true file system. Instead, we have a collection of 25,000 some odd files that are 4 megabytes in length. We populate those with our survey data and our burst data. For our survey data, we accumulate the data until the file fills, then we close the file and roll over to the next one. So this is where our different types of files come into play. So we have a set of files that have no data in them that we care about. Those files are free. If one of those files is available, we go ahead and select it as the next file to use and start to write the new survey data into that file. The same is true for burst, but when we're in burst mode, we want to manage the time associated with those files. So we have a 10-second cadence for that. We generally have managed our size of our science data product to fit within those 4 megabyte files so that we roll them over on the cadence. They're not completely full, but they're typically relatively full. Just recently, we did see those files actually fill on orbit, and our automatic recovery process is to close the file and open the next one, and we successfully did that on orbit. We also downlinked that data successfully, and the ground systems were able to process that data. So our mechanism for dealing with the possibility of overflow of those files for our burst data worked out just fine. So when we have files that have data, they can be in use, which means data has been recorded, but they have not been assigned to bring down to the ground. We also have files that are held. So on the ground, scientists can say, oh, this block of data is interesting, hold those files, and then they'll be scheduled to be brought down to the ground. When we're downlinked, then we free them, and they go back into the free pool. If we run out of free files, we end up using the oldest in-use files, files that we never decided were important to us. So we recycle those burst files in particular. We do automatically bring down all the survey data, so they don't get reused until they've been successfully downlinked. This is a little bit more detail on our physical implementation. So we have our TEMS, and over here we have our flight software. So we have the interfaces out here to the mass memory port of the system and our interface back to the spacecraft on SpaceWire. There's a lot of work that's done out here on the hardware side to format up the frames and send them over to the SpaceWire. Some other things is we have some fairly sophisticated data steering. So for example, we have data that we want to go into the burst data or go into the survey data, and we can alter that. We use that a fair amount, like during commissioning, for example, when we wanted to have certain data in certain files. So that allows us to do that. So this is a little graphic that shows that CFDP process. So we start off by sending some metadata. Then we send the chunks of the file, one piece at a time. And then there's a process here that automatically cycles through, sending each piece. As one is complete, the next one is sent. At the end, we send our end of file, and we get back an acknowledge from the ground. We can get NACs, in which case we resend the chunks of the data that are missing all the way up to the entire set of data. And then finally, we see the finish and the ACK fin here. Up here, this is also noting that it says delete the file, but I think it's mark it back to be free is a more accurate description. So that's kind of the end of that process. And so this process where we have had transmission errors and we receive the NACs, that whole process has worked very effectively for MMS. For the software side of this, we use the CFDP library, and so we go through a process where we give a request to the library, we give PDUs to the library, and we control the rate at which these things occur. Functions are invoked to send each PDU in turn. We register callbacks to see the status of things, the indication. On the virtual file store side, we have all these various primitives that we can use, and in the communication system, which is maybe the more interesting part, we have the way to open the channel, check the channel status, and then send the PDU. So this is the part that's cycling constantly when we're in operation. This is a little bit more detail about those functions. I think I want to go ahead and move forward because I want to get into the Cygnus stuff and the comparison of the two. So for our file system, we have our mass memory buffer index together with a timestamp to create virtual file names that we pass down to the ground. The hardware forms the file data PDU, and the software forms and responds to the file directives and produces the metadata, that sort of thing. So the hardware provides the configuration and start and end offsets in the mass memory buffer, and these are aligned. Once the playback is initiated, the hardware transfers the file data PDUs, and interrupt wakes the software task when a number of segments have been transferred. And the software task then calls the CFD library rate control function in a loop to match up the file read pointer with the segments that we've already sent on the hardware side. So that's the background on MMS. So moving forward then, Cygnus is a new mission that's just getting ready to launch. Instead of 4 satellites, this one is 8. These are small sats instead of the very large MMS satellites. This uses a fairly innovative idea of detecting the characteristics of the ocean roughness, which is related to the wind speed, by using reflected GPS. So we see the GPS signal at the satellite, and we can get time information. We see the reflected signal from the GPS, and we can do comparisons and determine information about the wind speed from that. So the purpose is to study the relationship between the ocean surface properties, atmospheric thermodynamics, radiation, and so on, to determine how tropical cyclones form and strengthen. So here we have a picture of the orbits associated with Cygnus that it's going to follow. So you can see that they're in a narrow band. They cover the tropical region, and we're able to see multiple reflections simultaneously, 4 per, and so we get a total of 32 measurements across the globe. The ground tacks are 90 minutes, and in the full day then we have pretty strong coverage of the Earth with these satellites. When Cygnus started, there was some question about whether or not we should use CFDP or not. We'd had that experience with MMS, and we knew we were, at the time that Cygnus was being designed, we knew that we were going to be doing CFDP with MMS, and we had some pretty good understanding of it from the integration process and testing process that we'd gone through. So we ended up doing a trade study because there was some thinking that CFDP might be too heavy for a mission like Cygnus. And so, there are a number of factors here that we considered. So how much would it cost to design it? How much was it going to cost to implement in the flight software, the ground systems, and so on? How much would it affect the flight software size, processor load, downlink rates? In the end, the team felt like there were more negatives to CFDP than positives. So it was decided that a custom packet relay protocol would be followed instead of using CFDP. And I think that there's a whole set of things. It's almost every factor. There was a perception that it was just a little bit not good. But then for the ground side, it was considered actually major, that it was going to have a big impact on them. So they didn't want to go down that path. So Cygnus also uses a hybrid hardware-software implementation. It also uses CCSDS space packet protocol and a simple sequential input-output scheme, which I'll explain a little more thoroughly in a following slide. So similar to MMS, we've kind of partitioned the activities where hardware focuses on one area, in this case playback, and software focuses on recording. So the software erases the flash blocks when they're no longer needed. I guess I didn't comment we're using a flash memory here, which I'll show in more detail on another slide. Writes the completed pages to the flash. The flash blocks will contain only complete packets to facilitate the hardware playback, so we're not doing anything fractional here. We also track bad blocks and chain together consecutive blocks to make playback easier. So the hardware does the playback with the goal that this would maximize our use of the downlink. So it pulls the CCSDS packets out, formats them up into frames and CADUs, and then sends them one block at a time. There is an interrupt to the software to help us track what's going on the software side. So I mentioned before that on MMS we had survey data and burst data. On Cygnus, it's been broken up into more pieces. We have engineering data, science data, and these are two pools of nominal data. And then we have raw science data, and we have engineering stored data. So we heard a little bit yesterday, I think it was, about the idea of storing some information about your system so that you can go back and look if something goes wrong. So the idea of this pool is that we can go back and find out the status of the system. If something was anomalous, so we've got some data stored there. But these are the main workhorses here is the nominal data. So in each one of these blocks, there's a number of things that are kept. So there's some information about which blocks need to be recorded next, which one needs to be played back, and you'll see a little bit more on this on the next slide, and other kinds of status information. And so you see we have one row corresponds to each one of the 4 different flash memories or partitions within the flash memory that I described previously. So it's essentially a circular buffer. So in this case, we have our record block pointing here at the top and our playback down at the bottom, and this represents the memory being empty and none of the blocks are in use. So this size is the individual specific size for one of those blocks. So back here, these are not necessarily uniform in size. Notice it just says, from X to X plus 1, Y to Y plus 1, without saying exactly how big they are. They're configurable to be whatever is necessary. So one of the design decisions here was the way we manage these things is by setting this in a certain way and leaving this gap. We don't have to have a flag to track when the buffer is full or empty. And so you see that in the next one, when these two line up, then we know that it's full. So that's a design decision that was made by the team for managing that. So we also need to track information about the storage system, and in particular the number of erase cycles and the position of the bad blocks. And so we have this table structure to hold that information. So this is not stored in the flash. Instead, it's stored in MRAM, which is a non-volatile technology, which means that if we do have a reset or some other event, the data will still be there for us when we need it. So in conclusion, we've had 2 different missions here that used different approaches to the file transfer. We used CFDP for MMS, and that was a reliable transfer. And that process has worked very well, and our contacts are fairly long at about an hour a day, and this has been a very effective decision. And for that sort of approach or that sort of a mission profile, we think that CFDP makes a lot of sense. For the small sat mission, a more simple sequential record playback approach was selected. A reliable file transfer process was not provided, and the conclusion was that the loss is tolerable, so the mission went forward with that approach. Another characteristic is that the contacts for Cygnus will be much shorter. So one of the things we see with MMS is there are these very long delays in the chain. So we start the process, and it will be minutes before it's acknowledged on the CFDP as it flows through the system on the ground. We would not even necessarily see those feedbacks during the time of the contact for Cygnus. So again, we just basically send it, and that's the approach. So we're not necessarily advocating that either one is better than the other, but just that should think about what your mission profile is and choose an approach that makes sense for you. Thank you.
Thank you. If anybody has questions.
Hello. You're using a circular buffer in your second approach, right?
Yes.
And your criteria for full buffer is when you have your 2 pointers at the same position.
Yes.
And that is not the same criteria for an empty buffer?
It's not the same for...
This is the same criteria for your empty buffer, right? When you have your 2 pointers.
Right. So for the empty buffer, they're off by 1.
Okay. Oh, I'm sorry. Thank you.
Yep. So I think it's one of the people involved in the design really didn't like the idea of the flag, and so this is the alternate way of doing it. It's a design decision. You could also just use a flag, right? So, but somebody felt really strongly that this is the way it needed to be done, so I pointed out.
Hello, this may be a little bit off topic, but they've been having some trouble launching it. Do you know what kind of failures they were having?
So there was a problem with the deployment process on the first day. I know that one for sure, and then they're still deciding how to recover from that.
Yeah. I saw the latest news report says they've got a window opening. I think it's Thursday.
Right, I understand that it's rescheduled for Thursday.
Yeah, okay.
Yep.
Just wondering if you knew anything. Thank you.
All right. I guess that's, is there any more question? Nope, we are on to the next talk. Thank you, Paul.
On schedule.
Thank you. You have a good day.